Welcome everyone to the channel again. And today I'm going to derive an expression for the Euler buckling uh, for column uh, when the two ends are pinned. So we have different boundary condition, but like in this video, I will going to explain just about the pin condition and stay tuned because in my other videos I will be going to derive the expression for other boundary conditions as well. But when we talk about the Euler buckling formulation, in order to satisfy the expression, we have some assumptions. So those assumptions are made basically to make the derivation, you can say, easier or make life simpler, because the empirical formula which we'll derive at the end of this video, that is only valid only when these all assumptions are satisfied. So in this figure on my right hand side, you can see there is a column which is named as A and B, and a compressive load axial force PCR is applied at the top end A, and the total length of the column is said to be L. And PCR is exactly a load which is called the critical load. Um, so if the P applied force is greater than PCR, then only you will be able to see the deflected shape. So the deflected shape is the red dotted line. Um, so when the applied force on a column, which is a compressive force, exceeds the critical values of the load, then only you will be able to see the buckling shape. Now the buckling shape is also going to be different for different boundary conditions. So in this condition, as you can see, this is parabolic, and we have some slope at this point A and point B. Now the assumptions here I have already highlighted. So the most important part is the column should be made up of homogeneous material, right? It should be homogeneous in nature. Now the material obeys Hooke's law, so it has to be within the elastic limit. Next, the load PCR, the PCR, it means the critical load should always be acting at the center of the column. So from the top view, if it's a rectangular section or if it's a circular section, so the red dotted line here is called the centroid. Uh, so this is called the centroid. So in this case, this is the red dotted line. So it means there should not be any eccentricity when the load acts at the column. So it should be always acting at the centroid of the cross section. And then the column should only buckle in one plane. Once you satisfy these all assumptions, then only you are eligible to find out the expression which is valid. Now, from the figure here at the top, I will be going to get the free body diagram. So, as you can see, x is a distance which is calculated from the top AB. Now, if I draw the free body diagram, so this looks like this because it's already buckled. Now, right? And so we have the applied load here, which is, I'm saying, mm, let's say it's PA, right? PA, so applied force. Um, and here, the magnitude of deflection is P. Perfect. Now, since the body, the column is deflected, in order to keep it in equilibrium, an anticlockwise movement is generated here. So this is the anticlockwise movement generated here in order to keep the body in equilibrium. So for my investigation, so this clockwise movement is positive anticlockwise is negative. Now if I try to derive the expression, so we have PA multiplied with P, which is anticlockwise, minus moment is also 0. So this we got when we take moment about x is equal to 0. So x is at a distance. So at this particular distance x, if you take moment, so we have PA into P. So this force is anticlockwise perpendicular direction, and this mm. Now from here we have m is equal to minus PA dot B. Now keep this expression as 1. Now from the moment curvature relation, we have moment curvature relation, we have m by EI is equal to d square by dx square. Now here B is the magnitude of buckling, right? So that's along the y-axis. Now replace the value of m here. You have minus PA dot P EI equal to d square B by d square. If I simplify this, d square P by dx square plus PA dot PA EI is equal to 0. Now this is called second order homogeneous equation, right? Because this is in the form of y double dash by dash plus cy is equal to 0. This is the uh, expression how the second order homogeneous equation looks like. So here in this case, a is equal to 1, b is equal to 0, and c is equal to pa by a, right? If we do the similarity check between this expression and this expression. Now, from here, we can write an auxiliary equation. So, auxiliary equation can be written as r square plus pa by ei is equal to 0. Now, r is plus minus pa by I is the imaginary number, because when it goes to the right hand side, so this imaginary number is I square, so I a by a. So in simpler form, r is equal to plus minus a by ei to I. Now we can say this is in the form of ai, a plus ip, where a is equal to 0 and p is equal to pa by ei square root, right? Now to get the general solution of the auxiliary equation. So if we want to find out the general solution of the auxiliary equation, this one, we can say V can be written as C1 cos Bx plus C2 sin Bx. So this form should be e to the power ax, or if I will give you the generalization, this expression is in the form of e to the power ax c1 cos bx plus c2 sin bx. Now a is equal to 0, so we get c1 cos bx plus c2 sin bx, where b is equal to this. This is b. Now, how do we find the expression for c1 and c2? We want to find out the value of c1 and c2. To do that, use the boundary conditions, right? So if you look at the column here at A and B, so exactly at A and exactly at B, the deflection is 0. So we'll write it in a sense that at x is equal to 0, B is equal to 0. So if you put the boundary condition x is equal to 0 and v is equal to 0 from equation 2, we get left hand side is equal to 0. This is c1, 0. So c1 is equal to 0. Now we have another boundary condition at x is equal to L, v is equal to 0. At x is equal to L, v is equal to 0 means at x is equal to L at this point. So at the bottom and at the top, the magnitude of v is 0, right? Now at x equal to L, so we have v is equal to 0. We already get c1 as 0, and then we have c2 sin bl. Now this is going to be c2 sin bl is equal to 0. Now this is going to be a bit tricky here. Now here, either c2 has to be 0 or sin bl has to be 0, right? Either c2 is equal to 0 or c2 sin bl is equal to 0. Now if c2 is equal to 0, p is 0 always, because c1 is also 0. If we assume that c2 is equal to 0 and you use the value of c1 and c2 in expression 2, you will see the deflection is always 0, which is not possible because we are here to derive the expression for the buckling. Now we have another choice left. So sin bl is equal to 0. Now bl is equal to, for sine, this is n pi. So if I draw the quadrant, so this is 0, this is pi by 2, this is pi, 3 by 2, right, 2 pi. So if n for n value 1, 2, and so on, it's going to be 0, right? So n pi, so 1 pi in this quadrant, and then 2 pi on this quadrant, again in 3 pi this quadrant, again 4 pi this quadrant. So sign value is 0. Now we have p is equal to n pi by L, but b is given by PA by EI. Now the square goes there, and squared by L square. So we can say PA is equal to square by square EI by L square. Now this is the expression for column with pin boundary condition. Thank you for watching.